slides and audio. Oh, so it doesn't show me. Okay, so I can scratch and do things like that. Okay, so you're not going, none of us are going to be on this. I mean, our faces, so that'd be pretty good. It's on right now. Okay, so let's get started with the optimization and scalability. This section is supposed to last 1 hour, and the lab's going to be 1 hour too. And that may fluctuate in terms of how much time we spend where, depending upon how far I get. So there are something like 50 slides, and so that's quite a few. So yeah, so some slides I'm just going to go over very quickly, and others I'll spend more time on. My name's Kent Milfeld. If you want to get in touch with me, that's milfeld@tac.utexas.edu. And what I do is go over some things about the philosophy and motivation, about why you would want to time things and benchmark things, and why you would want to look at the scalability of those. And then we'll establish a baseline of sort of things you should know about and understand. That's the metrics, and then sort of models for doing the measurements. And then the important thing here is we'll look at what's happening on node and talk about how optimization should be there. And then we'll look at doing it across multiple nodes, because that's the big thing. You get about 16 cores on a single node plus an accelerator, and you might want to scale past that. Certainly, with a supercomputer like we have, you'd want to use more of one node. Okay, and then we'll look at some of the MPI internal aspects, the things about that you should be concerned about and know about, and when you're doing programming and when you're doing measurements to see how good your performance is. So, motivation. We all want to actually reduce the time that we have to do work, or our applications have to do work. And one of the good things about reducing that time is if you want a bigger system to increase the capability by reducing the time for your model or whatever you're normally working on, you can actually work on bigger problems. And that's the big thing. Supercomputers, we want to do some super science with that, be able to track, to simulate atoms, hundreds of thousands of them, millions of them, possibly billions of them, billions and billions of them later on. So that's the motivation. That's where we're headed in terms of supercomputing these days. And what we want to do is begin with some ideas about performance and measuring performance. And some people think it's just gigaflops, but certainly you can do gigaflops, and certainly with types of problems, the complexity. Let's see if I can get the pointer here. Oh, this pointer is a little bit hard to work with. One of the things is that if you know the complexity of it, how it scales, like a matrix multiply, n squared type of data, n cubed operations, and you have some feeling about that, and then you can have a simple model and you can scale up, and understanding the number of operations per second or gigaflops or teraflops is certainly good to measure things. Others, it's not so obvious, and the best thing to do is to measure some result that you're getting. So for instance, in biochemistry applications, they'll give the results of how good their application is performing in terms of the simulated nanoseconds per day or something like that, a day of computing, okay? And so there's different ways you designate what your performance is. And so have a clear picture of that in terms of what you want in the end. If you're working on a library, you have to understand the complexity of it, and if it's matrix multiply, how it scales. If you're working on an application, the bottom line is the results. And what may change there is the algorithm. Some guy may say, oh, it scales this way, and I get this performance in terms of gigaflops, and this other way doesn't get very many gigaflops. But if it's a matter of being a different algorithm and being much faster and getting your results back to you, that's the bottom line of what you want. Okay, and so what we're going to look at is a single thread performance, and people think just because they optimize your serial code, or that what we call a serial code, or that's going to actually work out fine in terms of scaling up, in terms of parallelizing things, but that's not necessarily so. And so what we're going to do is lead you, say, to possibly 4 steps you would take here on your route to developing code to run on multiple nodes, developing your code to be parallel from a serial code. Okay, if you're already working on a parallel code, of course, you could skip some of these steps. But if you have a singular a serial code you're working on, the first thing to do is just try running that on the node. Just, you know, one task or as a serial process on the node. You run that and see what your performance is, and then possibly do some optimizations there. But the realistic problem there is that when you go parallel, you're going to have to share resources. Those resources being memory. They'll also be the cache, the L3 cache. Usually, for each core on the node, it has its own L2. But certainly, you're going to be sharing that. You're going to be sharing an L3 cache with other things that are running, and so you optimize this code to run serially. But when you want to have a better feel about the problem when you have multiple, you're running across all cores. And the easiest way to do that in the beginning is just take that serial code, you have 12 cores, and launch 12 of them. And then time it then and see if it really slows down or what. And then you'll have a better idea of the resources it's trying to share. You know, if it's memory intensive, then if they're all trying to share that memory, your performance, the same time it should have taken for one is going to be a lot longer for all of them because there's contention and they're trying to share things. So that's a real simple way to get going. Try one and run 12 of them. See what happens there. Gives you a little bit of idea about what's going on. But of course, that doesn't. You may not be able to do that if it's a large serial code and taking lots of memory. Okay, because you only have about 2 gigabytes per core on these systems, and that's a good thing to remember. That's your limitation there. And then the next step is single node parallel performance. And that might be where you're running all MPI tasks. You took MPI, you know what that's all about, all MPI tasks. Or it might be a single MPI task with threads under it. Okay? And why you're saying one, why not just do threaded? Well, if you're going to scale to multiple nodes, you want to have an MPI task here with its thread on this node and an MPI task over here with its threads over on this node. Okay? And the situation may be you want maybe 2 MPI tasks per node because we have 2 sockets there. Okay? And they both have their local memory, and we'll see more about that in a bit. So the next step is actually doing the parallel on the node and doing some measurements there. You don't have to go to multiple nodes. And what's really nice is we have this utility IDEV that lets you get to a node interactively and do computing there. We didn't have that before, and when you wanted to see results and stuff, you'd have to put it in a batch script, submit it, and wait, 3 or 4 minutes to get the results. Now we have IDEV. Instantaneously, you're on a compute node, and you can do your calculations. Okay, and then the multi-node, that's where you're usually headed. There are lots and lots of things that can decrease your performance there, and we'll talk about some of that. The other thing is in terms of motivation and philosophy, is if you're benchmarking and developing a code, and of course you're worried about it being correct, and you should always watch that every time you change things. Am I getting the correct results? But the other thing is you come back later on and you want to run a code or look at something, and you don't have any information about that. You've lost the details. What was the environment? Did I do a module load there? which compiler did I use? Forgot which compiler I used to compile this. So one of the things in your development directory, it's good just to have things in there that you can refer back to later on. I typically put a source me file in there with all my environment variables that sets them, that does the modules. So when you come back later on, you refer to that. It's not something you wrote in a book and you can't find it later on. It's right there. So that's one good thing, is just have a source file in there. I keep an info file in there, a file that has all the information that I used, and of course you have a make file. And you can include other things there that have information to, say, for execution. All my directories have this thing called do this in there, and that's how I launch the file. Okay, so you have information about your environment in the info file that has compiler information in there, things you might have tried, and it sort of outlines everything there. And those are important to have around. To do this, to say the exact commands you used a long time ago. So those are good things to have around. Of course, you have to make file there too. So keep accurate information. Use those scripts to do this or whatever to launch things, and so you can remember exactly how you did it. I'm speaking from years of experience in not doing this to tell you, yes, it does work. It's pretty good. And another important thing is to start thinking about affinity and where things run, especially with heterogeneous systems like we have here. You want to keep information about and worry about where you position your task on the node, those MPI tasks. And you also want to repeat things. If you do a measurement, don't just take one measurement and say that's good. Take 2 or 3 measurements. Make sure you get a good average, and then you know the variability. And some of these codes can vary quite a bit. So the hardware, or the prototypical node that we have here, consists of these 2 sockets here, one on the left and one on the right, and some sort of interconnects. And you as a developer worry about these things. Worry about these things in terms of, well, when you're programming, you have to, and when you're running applications, you should be concerned about where things are running and what's the potential for them. How big are the caches on these systems? So you're always, to some degree, worried about or should know about the hardware. So in this example, I show what we have on our system, and that's 2 sockets, and each of these sockets has 8 cores. And what you notice right away, on the left socket and the right socket, it has a line out there, or a connection or channels out to the host memory. And these are what we call SMPs, symmetric multiprocessing nodes. And what do we mean by symmetric? Symmetric means that any core that's running an executable or something has equal access to the kernel. Symmetric, and that also implies there's one kernel running there. That also implies that any core or executable that's running on the system potentially has the ability to access memory any place. So if you look on there, I have 2 memories and two sockets. So how can they access each other? If I have an executable executing on the left, how can I access the memory on the right? It actually goes through an interconnect between the 2 sockets. These are their memory controllers here. These are memory channels, and if I'm running executable on the left on one of these cores, I access the memory usually over on its local memory over here. But that doesn't have to be that way. There's situations, which we'll explain later on, in which you have memory. You might have, for an executable over here, its memory, or its data located in the memory over on the right side. In that case, it has to go through this intra-processor or intra-socket connection here over to here. And it has to do one hop. And then the situation is as well, okay, so that means a little bit more latency if you're not using the local memory. And it also means maybe the bandwidth won't be as good because the bandwidth for this connection may not be as great as this. And we'll look at those numbers later on. So you have a bandwidth thing, a rate thing affecting you, and the latency depending upon where your memory is going to be located. And those can be important in terms of the calculation. To first order, lots of times, not that much, you know, but it could be 50%, 60%, or even more, depending upon certain right circumstances. Okay, so knowing what your node looks like is a good thing. We also have connections here to what we call IB interface, InfiniBand. That's what IB stands for. They call it HCA, host channel adapter. They used to call it a network interface card or a NIC there. And so the new terminology for InfiniBand is HCA, and that's how we get out to the network. Okay, so that's sort of interesting. I get out through the network. I have to get memory from here, and it has to go through here and out through the network if we're doing message passing, right? Is it going to be a little bit slower for things to come over here, out through here, across here, and then out through here? You betcha. Okay. So if you just have one single task in the MPI that's doing the communication, you want to make sure it's on the socket that has that connection to the interface. Okay. So there's one story right away. Hopefully we'll have lots of stories for you. So on node scaling, when you're looking at the serial performance of that one guy compared to multiple serial performances on that, you'll start seeing, you should see some differences depending upon, that might be attributed to the L3 cache, having to share that, and of course if it doesn't fit in cache, then it's going to take longer to compute, or you might have all of them accessing memory extensively, bandwidth limited type of application. You'll see that right away. You know, you might have thought the serial would be slow. The parallel on doing that is going to be incredibly slow, and in which case you might do some sort of hybrid method. That sometimes can help for doing things. So, and just because you make the serial code faster, that doesn't necessarily mean that that fastness is going to be the same, of course, when you scale up. And something to think about is, instead of storing it back to memory, if it's easier sometimes to recompute as you're going along, then that's a good way to do things. And actually, the quantum chemistry packages a long time ago used to write things to disk, and then they had the direct method in which they said, oh, we'll just, the computers got so fast, they said, we'll just recalculate that on the fly. And that really, really did work. Well, you could do the same thing for memory. Probably not as big a gain as that, but that's a possibility, especially when you have to wait quite a few cycles just to get access something from memory. And of course, how many streams you have accessing at memory may be important in the parallel code, and you might want to actually take these loops and split them up, and that might run a little bit faster because then each loop simultaneously, as they're running the same part across all the tasks or all the threads, will not have that many streams to memory, and things will not be, quote, choked up that way. Okay, so some of the feeds and speeds that we have on our system here is 36 gigabytes per second to local memory, and 36 on this side for this local memory, left and right. And so add those up, and it's about 75 gigabytes per second. Okay, so something to remember when you're thinking about doing things on node or doing things off node is that if I have it in memory on node, I'm doing some sort of communication, you're talking about 75 gigabytes per second shared among all 16 of the cores here. If all those cores are trying to do communication over to some other nodes, that's 16 cores trying to go through 6 gigabytes per second across there. So if you look at it, access to your local memory is going to be about 10, and it always is, it's about 10 times faster than communicating out through a different node. Okay. Not only that, but the latency is tremendously more, you know, in the order of tens to, you know, up to 50 microseconds sometimes to get across, you know, in realistic part. You know, they claim latency to get across the network from one node to another node is in the order of a microsecond. But when you're doing inside your code, when you're doing all these other things, it's not going to quite be that good. And so, you know, you're talking in the order of tens of microseconds compared to nanoseconds of getting things out from your memory. So those are good things to remember, sort of ratios of you know, speeds and feeds between your sockets. That's about 15 to 20 gigabytes compared to 36. So you can understand if I'm trying to stream something out through here through memory, it might be bottlenecked here, be bottlenecked by this. Okay. But certainly the big bottleneck is over here, but this is going to be a hindrance when I'm doing memory access across from this core over to this memory core over on the left to memory over on the right socket. So that there's going to be, you're going to have a latency, one more hop, getting through that, you might say, local mesh, and then you're going to have that bottleneck. And depending upon how much you're trying to get through there, it's going to be slower. So you can well imagine local to remote access is going to be about 20–30% difference. Okay, so you keep your stuff local. That's the news there. The Stampede processors, the Xeon E5, these are the speeds and feeds. Just to give you a feeling about the you know, things you have to consider when keeping things locally, in the cache compared to going out to memory. If you look down here on the bottom right, you see accessing things or doing a DAXB operation, just multiply and add something together, and doing it out of cache, L1 cache, you can get about 33% of the peak of these systems out of there. If you're going to do it out of the L2, you know, that's going to be in the same order, about 10% of peak. Okay, so we had this processor, we had, you know, thought we could do 60 gigaflops, and now we're down to 6 gigaflops, just getting it out of the L2. And then if you go to L3, you know, same order there, you know, 6% or something like that, but probably 7. And then when you go all the way out to the memory, you're talking about probably about 2% of peak. So when you're pulling things out of the memory, you know, the performance is always pulling it out to do just a couple
calculations. Your performance is going to be dependent upon that memory speed. So number one, if you're buying computers for somebody, or you're in charge of acquiring a computer for your organization, and they're running certain types of applications, know what that application is. Is it memory bandwidth? In which case you should buy systems with good memory speed. Okay. So the important point here is that when you're doing things in the cache, you don't have much room. If you look over on the right, our memory is 32 gigabytes on the node. And if you look down in the L1 cache right here, data cache, where things come in and stay, and that's what you want to reuse, what is that? That's 32 kilobytes. That's 6 orders of magnitude difference in size between what's out there and what you can have locally. So that's a big management problem right there. And so that's why we have the cache hierarchies, and then we might have 20 megabyte L3 cache out there. So that's why they put the hierarchy in there. And then this information about the flops, this is basically a number of flops you can do while you're waiting around for data. Data, of course, is lots of times prefetched, and you have streams coming in. But if you have these hiccups and you just sit there and you now ask for it and you have to wait, then these are the kind of times and the amount of operations you could do. The times in here, or the number of cycles, are listed up here, which has been about this, 2 or 3 cycles to get things out of L1, 12 cycles to get things out of L2. That's actually pretty low. And then 175 to 350, that actually seems a little bit low, at best, to get things out of memory. And you can do 120, 200, or up to 3,000 flops of floating point operations in the time it takes that you're stalled there waiting to get things out of memory. Okay, so memory stalls are important, and so that's why in some calculations doing prefetching is important. On node scaling, the important thing here is that we're going from aggregate serial to actually doing the parallel on the node, and in that respect you have to make sure everything is reasonably balanced. So when you put everything together in single code and say do it parallel, you have to worry about balancing it. If it's data parallel, where you just each take a little section of the data and work on it, that's pretty balanced right there, but things can get even out of balance there. So when you're splitting it up, if it's not even, then you got to make sure it's spread out even. So if I had three cores and I split up 10 things to do, I can do 3, 3, 3. And one of these has to do that one, and so they can all do that in parallel, and somebody has to wait on that other one. Okay, so even in data parallel, things like that happen. Or when one of those cores is actually accessing, say, memory on the other on the other socket, and that one's going to be a little bit slower. So things can get there's a lot of opportunity for things to get imbalanced in these types of calculations, and so working and making sure, and that's what I was alluded to before, making sure they're balanced is important. And let's see here. That's what I just described the situation in terms of memory affinity and problems there. And then you always have to worry about communication costs. And even though one core might be communicating to some other processor or other core on a different node, and you have 3 or 4 doing this, one actually may take, may actually have hiccups or delays in that communication acknowledgement stuff because of just a quick storm, and so things can get out of balance. So there's even in communications, things can easily get out of balance, and so you've got to worry about the imperfections, even though it may look data parallel. Perfectly parallel, there are things that can get it to go out of balance. Okay. And some of the other things are things to be considered is that when you are working with Amdahl, you're always working with Amdahl's law, and it's that serial part that's going to slow things down in terms of scalability. So when you scale up, you saw earlier that Amdahl's law can hurt you when you're scaling up to a large number of processors, and even if your application's 0.99 parallel, that can still create a problem when you're scaling up. So you want to try and parallelize everything, but also remember that when you're scaling up, lots of times you're making the problem bigger, and that's a different type of scaling. We'll touch on that in a little bit. So some of the things that actually cause serialization is things, of course, are not fully parallelized. When you're doing I/O, usually lots of times one processor is doing that I/O. That may be the rank 0, reads something in, and then broadcasts it to everybody else. Sometimes that's the most efficient way to do it. Well, that one processor reading, or that one core reading that file is a serial step. And then, of course, there may be dependencies. Even though you do things and make things parallel with threading and OpenMP,
there's still going to be dependencies in that algorithm in terms of some things might have to be done. Just think of in terms of doing a reduction. Of course, we got ways to get around this, but if you are just a sum of something, and if you put a lock on it that only one person can touch that address space at a particular time, that's a serialization. Anytime you put a lock or critical region on an area, that's serialization. That's going to slow it down. Okay, so you want to try and avoid those situations. And then actually to do the balancing, so there's different ways or different things that contribute to that. And you might have something in the beginning that you're coding up and it's naturally unbalanced. You might have something that eventually evolves into being unbalanced. So when you have adaptive mesh refinements, you have a place, you know, you have an equally spaced mesh someplace, and you're doing calculations on those, and they're divided up among the different cores. But then at some point, the calculation will realize that it needs to refine the mesh, make it finer, so it can have that accuracy. Well, that core is going to have to do more calculations, and you might have to split it up later on and rebalance the whole thing, which can be a problem. You have molecular dynamics calculations in which particles may aggregate to something or be attracted to an ion, in which case you might start out with a nice distribution of particles, but then later on the distribution is not equal in all parts of the grids, and you'd have to do more calculations for the core that has those extra particles in it. Of course, the other ones would be idle. And then you'd have to do a repartitioning of your grid, and that can actually take time too in the calculation. Okay, so there's different ways to look at doing things. There's MPI tracing tools. You can put insert into your program measurements, timers in your program. Lots of people do that on critical parts. And one of the things that's a little bit difficult to determine is just an imbalance in a parallel situation. So if I have something in a code and different threads are working on that, if I measure them and they're all, say, take 5 seconds, does that mean that I'm really good, that it's a balanced problem, that everything's working fine? It may not be, because if this guy took 5 seconds and it started on the wall clock time over here, and 20 seconds later this guy finally got to do his 5-second chunk, the whole range here is going to be 20 seconds. And so we've got this problem that there's an imbalance, but even though we measured what each task was doing individually, we didn't see that imbalance, and it could be caused for any number of reasons. And so that's why the guy who developed these slides put this in here, and I think it's a pretty good idea. For OpenMP codes, a good way to measure this is here's the code that we have down here, a simple do loop, a simple do loop here, and then we parallelize it above. And one way we do here is of course it would be different, but you can run this statically and it's chunked. But what we do here, just to make life easy and show the point, is we say we want 16 cores, 16 number of threads, and we request that in this OpenMP statement up here, and that's what we're going to parallelize. So we'll get 16 threads right here, right? This is the easy way to describe or designate how many threads you're going to use. You don't have to do it with an environment variable. You can just hard code this in here. And then what we have here is a do loop that's going to be work shared among all the threads, which means if we have 16 threads and the loop size is 16, when it work shares, each iteration will be assigned to one thread, right? That's OpenMP. Okay, and so what we can do up here is start our wall clock time, and then after we're finished down here,
we find out what the wall clock time is down here. This is being executed by a single thread here. This coming here, the threads all get forked here. They come down here. Single thread comes out of here. That's a barrier point. And then you get the wall clock time. So we've got now the range. This is good. We're going to, you know, the extremes for this. I'm going to start up here and start down here. We would hope that that's 5 seconds and a little bit, and all these other ones are just 5 seconds. But the situation, in a more complex situation, it may be that these tasks right here are getting started off differently. It could be that some are taking a lot longer than others. And what we do here is measure the individual ones. So now we have the range, we look at the individuals, and we get the maximum everything's taking, and then we get to see the variation along these. So this is the way to actually do performance evaluation, you know, in parallel. It's not just one wall clock number. If you're worried about imbalancing, it's actually looking at what everybody's doing. And it takes a little bit of time to put all this together and do it, but it's if you're going for the performance or you need to understand a certain area, this will certainly work out for you. So as we discussed before, the latency is lower and the bandwidth is higher when you're doing local access to DRAM. And I never explained yet how, you know, this memory gets assigned to the particular DRAM there. And if it's not here, it's a few slides later on. But there's a memory policy in place for assigning where, say, a data array that you allocate gets put. Okay, so you have your code, you have a dynamic allocation. You know, you have a malloc in C, or allocate, or an alloc in Fortran, and you are asking for that memory right there. That doesn't mean you get it in physical memory any place. That means you've asked the operating system for it, and it said, yep, I've got room enough, you can have it. Okay, it's just saying you can have it. Now, when the first time you touch that, you assign a value to, say, an array, what happens is the OS finally wakes up and says, okay, now I have to put this in memory someplace. And so it says, where are you doing your assignment, the core, and which socket, and in that socket, I will go ahead and put the data in its local memory. You can actually change that policy. You can change it to a paging round robin. You know, so you know it's a policy. You can change it, but the default policy is the first touch. Okay, and so that can be significant in calculations because what do you do lots of times in a serial code or in an OpenMP code? Lots of times, because it's the easiest thing to do, you may allocate your memory, and then you may initialize it not in the parallel part, but you may initialize it in the serial part. Okay, what happens when you allocate that in or assign those values in the serial part? You're working on one thread, right? That thread's got to be on our system on one socket or the other, and so that first touch memory, and when it touches, it's going to move. It's going to be in that local memory over there. Now, when you go down to the parallel region and it splits, say, across those threads, threads in the other socket are going to have to go across and have a latency to go over to the other side. So the basic idea here is that if you do an initialization, you want to include that initialization in the parallel region. Okay, do it in the parallel region, and that array that you're doing the index looping over. Okay, you do static allocation. Those threads, you'll get threads 0 through 15. Thread 0 is always going to take the first part. It's always going to be in that local memory, and this do loop of the parallel region, and then this do loop down here, and then next. It's always, if you do static type of scheduling, not allocations, static type of scheduling, it's going to be the best, and it's going to be memory friendly, and it's also going to be cache friendly too. Okay, so there's a reason to do your initialization in the parallel regions with OpenMP, and roughly sometimes it's a factor of 2 in terms of the degradation if you have to go across from to get remote memory in a NUMA situation like that. Then there's a part about assigning the task. In assigning the task, you can use NUMA control, and underneath in TAC Affinity, we do that. In the NUMA control, it's underneath what we're doing is saying, start executing a.out on this processor as one of the tasks, but we have this NUMA command in front of it that says which socket it's to execute on. And so that's what's happening underneath. We're doing NUMA control to do the assignment for you. Task set is just like NUMA control, except it doesn't have, you can't set memory policy with task set. Okay, and if you want to do things, if you're a person that's very critical about this and does a lot of benchmark, you can set it inside your code. You fork your threads, and then you get the thread ID, say 1 through 16, and you say sched set affinity. I want, if I'm thread I want it on core I. And so that's how you can do it in your code. You can do this within your code. You can do it as a part of your command to launch the process where you want these. And so there's lots of different ways to do this, and you have to be careful about mixing these ways. Okay, and as I said before, in terms of doing the memory affinity, we talked about that before. It's a first touch policy, and it's done in pages. Okay, so memory is allocated in pages, 4K kilobytes, and KI means 1024 as opposed to 1000. And so you can change the policy. Most people don't, and they want it to be local, and you just have to remember that it's a first touch policy that's going to be important. Okay. Things that actually get a little bit strange, things like doing transpose. If you don't do this right, of course, when you take a column here, say in Fortran, that's all in one memory, and you do the transpose, and it's changing the index, then that's going to actually be assigned, if you're doing an assignment, a certain way in a in the array that's receiving the access or transpose. And then the thing is, you'll probably end up indexing it as column-wise instead of row-wise, and of course that's going to be spread across different memories. So anyway, I don't have time to show the details of that, but be careful when you're doing transpositions in matrices, when you're taking a matrix transpose. Okay, so now let's talk about multi-node parallelism, and this is when you really get into using MPI, of course, and it's a distributed memory parallelism. And the network communication is usually a limitation, okay? That you got to go out through this 6 gigabyte link through the HCA, and sometimes that's just not enough for certain types of calculations. And increased likelihood of having I/O problems is what people do is they have a serial code, and they open a single file to put, say, a restartup file, and now they parallelize it, and it's just they're just working on a single node, and they have 16 threads or 16 tasks, and they say, oh, let's just write it to 16 files. Okay. Now they scale up to multiple nodes, that's okay, and they forgot what they did a long time ago, and now they scale up to 16,000 cores. Okay, and you have 16,000 files on a global file system, and you're trying to maybe just write a little bit. That hurts. Even opening those up takes a lot of time. So in terms of I/O, you want to do just like you do in communication. You want to aggregate. You want to have just one thread or one task on that node writing out if you're using a lot of nodes. So that's 16 times less. And that's usually what you need to do, because if you start writing to files, 16,000 different files, a whole lot, and you will probably hear from one of the sysadmins, you know, that, hey, you need to do something about your I/O. Not so much because we don't have the bandwidth. It's we only have one server that actually takes care of the metadata for opening and closing files. Okay, and so you have to think about that. You have many different users on the system accessing files on this parallel I/O file system. And if you have 16,000 cores, and each one of those is continuously opening up and closing a file just very quickly for a restart, that's a waste of time. Okay, and it hurts the metadata server and slows it down, not just for you, but everybody. So that's why you usually hear from the sysadmin if we see this kind of behavior. So good reason to know about that and be careful about that. And then, of course, you get into imbalances just because the communication can get imbalanced. And you can talk about GPUs. And that, of course, when you have a heterogeneous architectures in one node, the GPU, you're computing on the GPU or the mic, and these two different sockets, that's a lot of different processors there. Okay, or in most cases it's two, and so you have to worry about the balancing, and that is non-trivial. When you build an application, say, for instance, the mic, and you do an offload, how much do I give it? That mic over there has a lot more processors. I have to worry about the threading, and they're also a lot slower. And then there's another problem. There isn't that much memory over there. So heterogeneous systems are a challenge. So, and, you know, but many people will take up that challenge so they can make their codes run much better. Okay, there's a high impact for load balancing in this case when you're using multiple nodes, and it gets even to be non-trivial to detect because now you've got multiple nodes. If you've got gazillions of cores, and we talked about the simple case where we just took the time, okay, there are applications out there that will let you take snapshots of traces of exactly how things are going, and that can be helpful. So usually take care of some problems on a small scale when you're developing, and that'll help you when you get to the big scale, okay? And again, the different reasons for doing that are different, working on boundary and local, the mesh size and all these different things we've discussed. So how do you do the load balancing? Lots of times it's just statically, and different architectures. You measure that things are going to be twice as fast, 1.5 times faster over here if I'm using this bunch of threads compared to this bunch of threads over here, and you just split up the work that way. That's the easy way. Lots of applications, reasonable number of applications use dynamic load balancing, where they'll change around they have to change around, or they may have fixed the interval where they do the rebalancing, or it might be always working on some sort of threshold. How many particles over the average I get in this particular grid or area, and they have different utilities, Zoltan, for helping to divide, to do the redistribution. And so there are utilities out there for doing that. We've seen this before, and we went through all the details that I wanted you to know about, except for one, and that is the speed of from the accelerator over here to on the PCI Express. Actually, I think this guy should be connected over here to this interface this way. But to get things from the accelerator or the GPU to another node, you have to go through, the idea here is that you have to go through the same network interface over here. So you might think, when you're thinking about, should I add an accelerator to my box or to my little system that has multiple nodes, and it's already communication bandwidth limited. That's the problem right there. That's going to be a big problem if you have on your accelerator on the mic multiple tasks over here, And those tasks are actually trying to get out through this interface over here. And that's one reason why we suggest people go to hybrid computing, is because, think about it, you have 16 cores here, up here, and let's say those are all, you have a task on each one. You're not going to hybridize it. Okay, 16 tasks. And those 16 tasks, when they communicate, when you scale up, are going to have to go through this InfiniBand network over here, 6 gigabytes per second to talk to all the other ones. Okay, and let's say you have nearest neighbor type calculations. It's not collective. Well, maybe that's not too bad. Okay, now you say I'm going to throw this mic on there, and it has 60 cores, right? And actually, you could put 4 threads or 4. You could actually put 4 tasks on each one of those cores. So you could actually have 240 tasks over there. Ouch! Or even 60 more tasks. Now, you're talking multiples of 10s, whereas before we were talking about order of 10 tasks on our node communicating out through the network to some other. That's not bad. And now we put this on here and we say, oh, I don't want to change my code. I don't want to hybridize it. I'm just going to put tasks everywhere. And let's say I'll live with 60 tasks over on the accelerator. Well, 60 plus the other, we're talking 75. We're getting in the order of 100 tasks here trying to communicate out there. So that might not be a good idea. Okay, so that's why in the future what we see is that the vendors are now coming to the point where they're making the accelerators and even the sockets with many cores on it. And so the thing is they're trying to pack so much compute power into such a small space now that they're giving up some of the more general aspects of the types of cores that they have in the host, the E5s, and they're making them wimpy cores. And what will decide what happens here is how many they can sell. So before, when they tried to, the market was set, they got to a point in the market where they couldn't make the processors any faster. Then they went to multiple cores. Now what they're doing is going to many cores, okay? And the big question is will the IT space adopt this and use it? And if it's good for them, they'll continue. I don't think they're going to make these just for HPC. So we'll see what happens here in the next 5 or 10 years. It'll be interesting. So this is my time was the many cores, the multi cores, and your time is the many cores. So that's what we're getting into. Okay, so off-node bandwidth. Have you seen this in one of the previous slides? Okay, so what we have here is for going a measurement, what we call effective bandwidth as a function of the message size. So down here on the bottom, what we're going to do is to say, let's take 16 bytes and ship it over to another node and measure the bandwidth we get for that. Okay, and then we're going to take a bigger message, and bigger message. And what we see over here on the left is the bandwidth that we get, and then for the message size. So when they talk about, and we talked about having a 6 gigabyte connection through the network from one node to the other node, we're talking peak. And it isn't always peak. It depends upon the message size. That's what this says. That's why, and in here it shows that, if I'm at 1 kilobyte or 2 kilobyte here, I'm about half the really peak bandwidth. So I'm really not using the resource to its maximum. And that's why they say when you're doing communication, try and aggregate and make your message size bigger, because when you do that and you're sending one as opposed to multiple, and this is what we'll do in the lab, you're going to be operating more on the top of the curve than, say, on the bottom of the curve. And so that's what that's all about. That's what we're talking about there. Then there is the communication on node. So you're doing MPI node to node, that's fine, but what about MPI on the node itself? Well, you really don't need to go out to the network interface card and come back in. You can just do shared memory types of things of data movement. So that's another story. And I just want to point out this dip right up here, and we'll explain that in a little bit. So the other thing is that things are always changing. The top graph, we're not going to go into the details, is just different measurements depending upon some sort of settings that they had at that time. And what you need to remember is that if somebody doesn't set things correctly using the right defaults, or somebody hasn't read the documentation, doesn't know how to set things up on your system, you may be computing down here or communicating down here as opposed to up here at this much higher bandwidth up here. This is what we have locally here, measuring on-node communication. On-node meaning, you know, you have two tasks on the same node. In one case, over on the left, we have one of the tasks. It's the sending task and the receiving task is on a different socket, and then in the other one we have them on the same socket. And that's just to show it's actually doing the exchange through memory and not through so much message passing. And the difference in here, from here to here, compared to over here, is the performance you see difference because of the way it's accessing memory, or it's going through the interconnect between the two sockets. And so you'll see a difference there, and that's okay. But if you're doing measurements and you're one time you're getting one result, and the next time you're trying to figure out how that happens. And here, you know, we're just exposing that, yeah, you're going to see differences, and it's not really that incredibly important, but it's good to know that these NUMA architectures have differences even in the communication costs. So there you go. So what we want to do now is go through, we'll go through this example, and then I'll quickly go through some other things at the end, but I wanted you to become familiar with this. It shows a couple points. So if we have a finite difference calculation, and we have this stencil that we're doing an update in, where we have a point here, and it accesses in, say, if this is I along here, this is I minus 1, and this is I plus 1, to get a value here, and then say J plus 1 and J minus 1 to get a value here on this grid to do an update for our finite difference. What we're doing here is, if you take this point, and this point, what you realize, and sit down and look at it, is that we're doing we're accessing two memory accesses, and for every update that we do. So that's pretty memory intensive right there. So that's the point about that. If we do a 16,000 by 16,000 here, what we want to do is look at the difference in the way that we might communicate across, do the communication for these ghost cells. And what do I mean by that? Okay. Let's see, do we have it here? No, I think it's a later one. Okay. In our update, and I'll show you how we set up ghost cells later on, but when we are going to do a decomposition of the data for which threads are going to be doing what, or which tasks are going to be doing what, how do we divide this up? Okay, we have this grid of points we're going to be working with, and we can do it in one-dimensional, where if we're taking, say, P of these, we just divide up which task for several rows, or quite a few rows, that it's going to be executing on. So if we have 10 tasks and 16,000, then we'll have 1,600 rows to work on in there. Okay, and so we did that one-dimensional decomposition there for our calculation. We could have also done that in two-dimensional. Okay, we could have split it up into little bitty squares as opposed to these long, thin rows here. You know, okay, either way, you know, it's the same number of operations, right? Okay, the difference is going to be in terms of the communication. and as you scale up, communication costs always are going to increase and be an important part of doing the optimization. And so if we divide these up here, we're going to have, in terms of the subdomain, there'll be n by n divided by p, where we divided this up. And we'll have this, we'll always have this long dimension n here in terms of the size. So we have this decreasing by p. We throw more processors, we have it shrinking like this. Down here, the size is going to be decreased by n divided by square root of p on both of those. And so the situation is that at one point, I mean, we always have to be communicating what's on this boundary here to this other task over here when we do our updates in a finite difference calculation. We always have to be communicating. And that's staying that's staying the same for no matter how small we divide this, okay? So we're going to just take the same calculation, 16,000 by 16,000. We're going to throw more and more processors and see what happens for the 1D and the 2D case, and then look and see what this looks like in terms of an analytic scale of what's going on. And so if you sit down and look at the projected speed up for this, you'll see that the one-dimensional case up around 4,000 processors really starts to slope down in terms of performance. You know, the amount of time it takes to get this thing back. But yet the 2D keeps going straight up. And one of the reasons for this is if you look at what the communication cost and the overhead is going to be. And here, so if we have the green is the compute part, the yellow is the communication, the bandwidth part, or what you're getting, or what the costs are for the communication. And this is a % of total execution time. So it's a little bit unfair because we're just taking this one problem and we're saying, let's throw one processor at it, and it's 16,000 by 16,000. And now we're going to throw 16,000 processors at it. Well, you really wouldn't do that. You'd scale the whole thing up in realistic. But this is just to give you an idea of why the 1D and the 2D decomposition are so different. And what we see here is a tremendous amount of the cost of doing the calculation by the time you get to 16,000 processors is going to be because of the communication cost in terms of %-wise. Okay. Now, if we look at the 2D, what we see here is that the communication cost is small, and what they did was separate out the overhead, meaning the situation of we have actually 4 instead of 2 communications, and there's an overhead for doing that. And what we see is we retain a lot of power for doing the computation here. Are we still doing a lot of computation compared to the overhead? So 2D decomposition turns out to be the winner in this case. And then optimization in terms of process, you all know about this. Find the hotspot, decrease, make it better, do a new profile after you do that, decide how much you want to get done, or how much more you want to optimize. Sometimes you get to a point where they're all the same, 5%, 5%. That's it, I'm stopping here. You have to decide whether you're going to do optimization for the rest of your life or do your science and get out of graduate school. That's what you have to decide. Okay. So best practices for doing things. So one, always check for correctness. Make your codes portable. Make them clear and simple. Not too many different subroutines or functions. You know, you have to have a correct balance in the layering. You can always do inlining, but you got to remember sometimes some of the processors aren't very good at inlining. And that actually helps in terms of optimization and allows it to, and you all had some ideas about vectorization. Don't forget in C, it's row major where you access memory. It's across the row that you want to access things. And so that's the outer bracket that you want to have the index go fastest over, because when you pull in from memory, you got to pull in a full cache line. Okay, that cache line, when you hit the first one, is going to get those other 8. If you're jumping and striding across that, you're pulling in a whole cache line to use one element. Okay, so that's very, very important in calculations. That on that inner loop, that you're, if possible, you're accessing row-wise in terms of that inner loop for C, and it's column-wise in Fortran. The other things are, of course, you want to make sure vectorization is much more important than before. You can get 8 operations per clock period now, and that's because and only if you vectorize the code. So it can do simultaneously those 8 operations. So that's a big thing. And of course, higher level parallelism is about doing simultaneously on a bigger scale. So certainly at the finest grain level down there, you want to make sure that they're doing these operations simultaneously. SIMD, and that's what they're referring it to now. They used to just call it vectorization. Now they're calling it SIMD. So you got to do SIMD now. Okay. And always help the compilers. You know, sometimes you have to write the code so that the compiler understands that it's that these are independent iterations. You can give pragmas and directives to say that it is now, so that's very good. They're not all standard. OpenMP is standard, and you can do that in OpenMP in terms of SIMD operations. Other ones you have to know the particular syntax for the directives for that compiler. Okay. Minimize use of pointers, and always in the hot loops, don't do any branching. Okay. Okay, so the 2 things I referred to earlier, and I just want to point out here, is that you can have strong scaling, take the same problem, and you just throw more processors at it. Or the more reasonable thing is you take the problem and you expand the size of the problem as you increase the number of processors. And that's usually the way things work. So the strong scaling and Amdahl's law, yeah, that's good. And that was always good for vectorization in the 1990s. But usually people are scaling these things up. And so it's the weak scaling that lots of people are very much interested in, because they're interested in expanding the size. Measuring things, you can always do that with timers. OpenMP, MPI have standard timers you can call. MPIP, IPM are 2 ways to easily get at the communication costs. And so when you're working and just beginning, that's fine. You don't necessarily need to do these that much. But when you're thinking about scaling up, you should really throw these utilities at them and look at them. Of course, you can get things for subroutines, prof and gprof. And then there are some other ones that you can get traces out of and see timelines of how things are done. That's good. Of course, you don't want to work with those on big scales, because these things consume a lot of, well, they consume some overhead, and then they will, to see the results, they would have to print out and have massive amounts of results to look at. Here's an example of a strong scaling in a situation where over on the left we have speed up, and on the we have plot that against number of processors. And of course, if things were perfect at 64, we would have speed up of 64. And what happens here is we see that the communication costs in this situation are overwhelming, and the place you'd really want to compute is someplace over here, the most efficient. You would go, well, how can we have these 2 points here? And that might be because of the cache efficiencies up here are better, and you get this super linear. That can sometimes happen. And so this is the usual situation that you'll see as you scale up to a point that it falls over, and it's important to know where not to compute. Okay. Communication and bottlenecks, some are inherently communication intensive. FFTs are like that. You could do things locally by making the on a node using OMP hybrid codes. Sometimes that helps. And as I said, the second part down there, pack data to send large messages. If you can, I/O gets to be a problem. And so the summary is you got file I/O, network latencies, bandwidth, and unbalanced workloads. You always have to worry about these things, and so that's that. Let me have about 5 or 10 more minutes here, and then we'll go in the lab, and I'll do some MPI internals. And you've already been exposed to MPI, and the point I want to get across here is that the message is usually blocking, meaning that it's going to stop and wait until it is finished sending that message, and whatever array that was in, it stops until there's no more activity on that array, and you are free to use it. Okay, so what happens if one task is doing the send? It stops right here till the send is completely done, and the other side, and this is supposed to be the other side, the other task on a different node, say, is posted to receive and actually got all the data on its side and finished, and then this guy says, okay, sends a message back, I'm finished, you can proceed. Okay, and so this is called blocking. This guy over here is blocking, but what you can always do, if that's getting to be big costs in terms of communication, you can always do non-blocking with the immediate send, immediate receive, and it will allow the process here that's executing this to fall right through. It says get it started. Some thread or something daemon in the background is going to take care of this for you, and that process that you're executing here will continue on down right away immediately. That is on the assumption, or it's making the assumption you won't touch that array until it gives you the clear that it's finished doing that. And so you can do other work, but it can't be on that array that you were sending from. Okay, that's the big idea there. So you can do work while it's the communication process that's going on. So that's pretty good. And in terms of doing the calculation we showed before, let me show this slide. This is what I mean about sending information back and forth. If those two blue areas were combined, that would be just a serial code. And now if we divide it into two, when we do our updates over here, we're updating from above, below, left, and right. That's fine. When we're doing our updates here, we actually need something over here in this purple area. So to make sure, instead of going and asking for it each single time with a message call, what we do is have a ghost array over here, and in that ghost array is just another column of whatever we're using here. And so before we start the calculation, we send it over here to the ghost, and we take this guy and send it over to the ghost over here. And now when we're doing our updates in this area right here, we just do a higher index, and we've got it. And so that's how the finite difference works. The algorithms work in that they have a ghost cell, or they call it a halo cell, and they get their information that way. That's pretty cool. And so the idea is you send them all over at one time. Well, the point I want to get across here is that if we want to do overlap communication, and we come to do our update and say a task over here and another one's doing it over here, the most reasonable thing to do is go ahead and do all the updates right here and get my update right here and start the communication over to here and let it go, and now I can do my updates here because I'm not going to access that array, and so now I can do all my updates here. So do the part for what you want to send over first and then start on this, and that's what this slide tries to convey up here. I had my kernel before where I was doing all this stuff, and I would do everything there, and then I would have my blocking communication below. Well, what you can do is have it set up so everybody's working on the boundaries to begin with, and then you set up your non-blocking communication. You're done with that. You're not going to touch it anymore. You may read from it. That's okay, because you're going to put what goes over to the other side in the ghost cell. You can read from it, but you're not going to write into it. and then over here you do have the rest of the compute kernel over here, and so now you can overlap the communication with the computation, and hopefully the communication takes less time. But anyway, you hide it, you've hidden it, and so that's the big thing about problems with latency, is if you can hide those kind of latencies by overlapping with some sort of execution, you're going to come out really far ahead. And so this is what the code would look like up here for that blocking part, and not, we did put it in here, but it evaporated, I think, from these slides. We had some other, oh, there it is, we did put it in, the work here. So you don't want to do the top one, because these are blocking, and what you would eventually have is to do the sends and receives immediate here. One, you know, of course, this is just two. It'd be a little bit more complex if you had more. And then these are immediate. You do your work down here, and then you do the wait down here. Say, am I finished yet? Am I okay? And then you go around in this loop like that. So that's pretty good. The other thing about message passing that's pretty important is what's evolved in the last, I guess, 6 or 7 years. So sometime back when you sent a message across a wire to another node, you could only go in one direction. And now it can do bidirectional. So now if it's rated 6 gigabytes per second, I can go 6 gigabytes here, but at the same time I could actually have somebody sending to me and me be receiving in another part of memory over here at 6 gigabytes per second. So this is the case where I used the blocking, and each one one does first and then finishes and then the other. And then when I use the immediate, which means both of them can start going immediately, this is the kind of bandwidth I get. And same looking profiles here, except over here, this is in the order of 6.5 gigabytes. And over here, I'm starting to get close to 12 gigabytes per second. So if you can do bidirectional communication on these newer systems, that's what you should do. Use the immediates and do bidirectional. And then what about that little glitch there? That little glitch is caused from the fact that you can have eager. They have 2 different types of protocols going on and ways to do it. And at low message sizes, they do one protocol. And at large message size, they do another protocol. And you think, well, why even switch? Well, the most efficient one, called the eager, just sets up buffers, and it just says, I'm going to send it anyway. It's going to go over there. It can go in this buffer. I don't need to confer with this guy over here. I'm just going to put it in the buffer and let him pick it. Give him a little message and let him pick it up. Okay, and so he can do it that way. However, at some point, you're not going to have enough buffers to support all the gazillions of messages that might go in, and so it gets to be a problem. And then over on the rendezvous, it has to say, are you ready? I'm ready. Pick it up, and it will put it directly into that buffer, or into that area of memory that it needs it. So, and actually, you can do the analysis, and you know, what's the latency? The message plus an envelope, you know, divided by bandwidth gives you the number of seconds it's going to do all this, so you can do this. And actually, eager, if it's already knows it's expecting it, doesn't even have to write it into the buffer, and it can just go directly in, and so you don't have to do copy messages. And doing the copy here is what gets expensive. That's why for the bigger one in rendezvous, you don't have to do that copy, and that saves time. And so the bottom line is, normally, if you just kept one protocol or another protocol, you'd get curves like this. And the best size, or the message size for the bandwidth for the eager looks like this, and for the rendezvous it looks like this. And so they have it change over right at this point. And of course, if they don't change over at the best point, you know, which could be done, it could not be set right on the system, you get this big dip down, way down like this, and as you're running a profile, and if your calculation's right on that dip, you're going to be, you know, it's not going to be so good. So it's good to do the profiles and just check every once in a while, see what's going. Okay, And so collective communications, that means it's not just point to point, but you're involving all the different processors. Avoid that like the plague. Don't do a collective communication unless you have to. Although sometimes there are good reasons, and some are somewhat simple, like reading from a file your input and then doing a broadcast. That broadcast connects to all the other tasks in the system and sends the stuff there, but it's better than doing the I/O on all those guys. Okay. So there's reasons when you need it, and certainly you'd use it, but if you don't have to, use the point-to-point communication most of the time. And then you've had this in the MPI, that there's a broadcast, there's a scatter, and these are all expensive, the all gathers and all to all types of calculations. And so, yeah, so the idea here is that the one other point, and then I'll leave you go. It turns out that sometimes we only need a group of tasks that need to share the information or do a collective communication. And what's very reasonable is to form a group just for that communication and just do the collective communication for that call, as illustrated here. So we have a large pool of tasks that we have from rank 0, say, to rank 10 here. And actually, we could do these in subgroups, possibly, the exchange of information. And if that's possible, what you do is form, say, 2 different groups and do the collective communication or some sort of communication just within that subdomain there. And that'd be much, much more expensive than in doing 2 across both domains. And so that's the other message I wanted to get across. And you can use topologies to do this, which all that means is instead of you doing the indexing of what is left and what is right and what is up and down, you can do this through calls to an API. And you basically say left, right, or up and down. And it will tell you, and it will give you that information to send. Because if you think about this in terms of if you have 100, or let's just take it easy, say on one node, and we have 16 tasks, and you divide that up into something like that square there, and you're doing this, how do you number those tasks? And what are their numbers? And then if 4 has to communicate with 3 and 5, or 1 and 7, you have these numbers right. And so, in particular in the ghost cells we were talking about, we send things left and we send things right, and the topologies make it real easy for you to access that information. And so it takes a little bit to set that up, but for a very, very simple case, it's fairly easy to do it yourself. It's good to do that once in your life, even if you're not a finite difference person, is to go through that. And it's fairly easy, and it's worth the pain. You get a little bit good feeling about networking costs and how it's all done internally. So bottom line, MPI internals. On-node bandwidth is not limited by the network. Expect fluctuations. Bidirectional is good. Aggregate your data into large messages. Avoid collective communication calls. Group whenever you can. And then, of course, virtual topologies are helpful. So we have a whole nother section, but we're not going into that. Okay, and actually, we're pretty close to finished. I/O. Multiple accesses to a single file is no problem when it's just a small number of tasks. Massive amounts of access to a single file is always a problem. When you scale up, of course, you run into an I/O limit, and then when you scale up, be careful about the sheer number of files. And so there are ways to get over this. Use NetCDF or HDF5 to do things. And future directions, we have threading. We always talked about 5 or 8 and 16 threads per node, 20, maybe bigger systems 40. Now we're talking about on the architectures, what's coming around the curve is even bigger ones in the order of hundreds of threads. You already see that on the mic. Hybrid codes are going to be more important, and you know, in terms of you can't hold on to MPI forever, and you always have to worry about memory space. And big thing you have to worry about coping with heterogeneity. And let's see, we got questions. That was a 2-hour talk in an hour and 25 minutes. So we have about 35 minutes for the lab, and this is good. And the lab illustrates the finite difference type of calculation and the communication cost, and it's somewhat dumb but very instructive, and it's self-explanatory. Pull out the page, pull out the PDF on the web, and we can get started in a lab. But if you want to stretch your legs, I need a little bit of coffee, so if you don't mind, give me 2 or 3 minutes, and then we'll get started with the lab. Okay, good.
This is the chat. Oh, good question. None so far. Oh, no, there are questions today. We're running from the Martin project. We're in the lab. Yeah, we decided. Yeah, we make a decision. It's the monitors. Well, that's the thing. I don't mind something keeping my face. No, you're not on your face is not on your. That's Square boxes. We were on the Google Maps algorithm that have all these. And I said, yeah. The really funny thing was really cool house story from silence and people review those areas. There's all these people out. Oh, really? And they got the rights to. Exactly. It is. No, not the first run they did. Yeah, they didn't reach. Immediately they were like, yeah. Yeah, there were a lot of people calling overweight, but he understands the target. The camera comes, see over things. Right. You know, things like this. There was the kind of drug deal. Did you see that? No, I didn't see that. These guys, they planned it. Because this truck kind of comes by once in a while. Apparently, we just saw it. You saw the truck coming, ran down, pull a sprint, and so they have this street that shows a series of things where it looks like this guy's on the street. Yeah. And then the guy running off on the elevator. Everybody's body. But then when you're way down the street, you see both of them. Oh, yeah. But they said it took like a year before somebody played about it. Yeah. That's it. Like a year before somebody noticed. What are people following? Yeah. Oh, yeah. What was the difference? So those aren't couplers. Those are Tesla M190s. Okay. Yeah, well, and no, those are, yeah. But what happened was the guy had a feeling, being checked for a guy yesterday. The guys, it's so old. Just one guy, months. It was one of the best hack sessions I've ever had. And we actually pulled it up, got it to the top. And the problem is, always need to do that. So the problem is, build it, and I tried to actually change the computer and make file. And the make file is make file. And there's no way how it he said it will work, right? Yeah.
think that even the easier the easier is the thing that makes it go ahead and ask questions. Yeah. So essentially, it's a simpler version of how it allows you to say, right, the problem. You know, big conference, jump over, we did that. You can do that. And that's what's cool about it. You do static routing, so wherever you look to go, there's no way. There's no way. I don't know, we're just gonna send this. Usually, there's you don't know how to do that. Exactly. Get rid of all the stuff, all that cool stuff that you should all in your head. Throw all that stuff away and just send the data. You see some of these, yeah, they can all look different. They goes off the side. Cats. No, he's not doing that. Yeah. And then,
if any of that like paid for coming in or something like that,
I did,
yeah,
thank you.
he's not on sale, 330. Oh, yeah, right after your, no, it's not very long. Yeah, that goes to free.
I never do that. You know what I usually do? I usually walk around with everything.
What are you actually doing on Stampede now?
Yeah. It's just a simple laugh, but yeah, I should do it. Ryan's got that already.
Email bounce back.
I always put it on it.
And over this.
Hey, Chris. So, people are going to say, "Thank you, wow."
Bring it down. Okay. Lost. And
that'd be good. Yeah, that's the good news. You guys have got to sign your toilet. Because nobody else, actually, I just did a whole. But that's reasonably, no, don't believe it.
I mean, you've been answering tickets for how many years now? How many of those things have been going? Yeah, I am.
You get all the yeah, I think that was a system.
Just not
Solve it.
yeah.
But I feel like someone else talked about that.
You see that, but that actually is crazy.
Oh, it is.
Because we talked about that a lot over the years. How we're going, there was a whole push in the knowledge base for the report. Hey, it comes in with answer, but 9 times out of 10, you never go back and look at Yeah, exactly. Change. Yeah, looking at that too. Let's talk about maybe doing like a live chat session a couple days a week. That would be open. And then ask whatever you want to do. Set on there.
Still a little bit good to be able to find myself.
I think what we have is so you get that call. Oh, I think it's good to have a
Yes. This is only certain packages.
Well, actually, what they're working on it, really small, doesn't matter, and now, but, yeah, how many people do about one? Is that one person?
But that person,
No, we have
Just for that, just for that guy. One person.
and then every day
New
is
person
different.
every day.
Actually, one thing I actually knew that. Yeah. He said, oh, okay, I see, I thought it was the man, because, you know, how long, you know,
Right. Once you're on the those people.
Yeah, essentially, yeah, about that. But, yeah, I'll go back and work on it tomorrow.
But I did last week.
Four, 5 times a quarter.
So it's not too bad.
Yeah, essentially, some of them are like, and some of them, let's try this.
My rates were $2.20. And nothing else. You know,
And that's all they gave you, and that's all they gave you.
the color is like resistance. Just use it.
But I guess better. Yes.
You know what I is.
Yeah, it's also it's one right? And they have the stack. Yeah. They have a week, but they also have the stack and the inventory on the it's so useful that had those
Yeah.
and
Yeah.
Yeah. So I just want this one that we typically don't go and see the in terms of
Yeah.
because partially because of so that you can't spend all that time optimizing something and the next day
Exactly. What's the optimization cycle?
Yeah.
How long do you sit in that loop?
That's
like once. That's it.
physics
Yeah,
once.
That's just what I'm mostly you're ready to you're ready when something to do. I think that's one of the see if I come right now, see that's going right in the words. See that
Pointers, classes, breakers.
Most of the stuff we use is in Python and Java. Abstract.
yeah, that's what you need.
Figure out price on all this stuff. Virtual machines, they're
Yes, it's not good.
No, I'm using power. Mine is tiny.
Yeah,
Mine's like this big.
that's what I was thinking. I want
Yeah, we have a MacBook.
yeah, I was
You think that's it? Okay. But no, I'm just talking about the physical size, so Pro, take that, the MacBook Air one, so. This small.
put in your space. Yeah, it's more. It's like this. Mine is. It knows nothing.
There's no GPU.
Well, yeah, I no, I don't know.
There's this tiny hole right It's a fan. No, I thought that was the body of the design. Obvious. I would stop accessing that for 10 years. They're 13 fan.
Yeah,
I got 24.
yeah, so, yeah. I don't know, like you said, now that you said that.
It really is.
That's a good thing. So I should do it. Yeah, actually, the. Oh, no, no, it's not tax. Mine's not.
That's great in here. Good here.
Oh, yeah, you hear that?
Maybe that's all it is.
That is?
Process turns on this call.
Yeah. Turn on the speaker. It was.
But you know what, when you're sitting there, right? You're sitting there, it's the word. This one I haven't really experienced a lot.
This one I recommend to the football.
I don't know if to gross.
I cannot put it in a
They're not called laptops, portables.
They're like designed to be under that.
Okay.
Do they really say?
Yeah, that's Apple. They're portable.
You don't want to get.
These guys do it.
This
No,
is
that-
like,
It also has a cheap line.
I think yeah, that's one they play.
And so any video you have a delay,
Roasted pie.
Roasted.
Yeah. No. Anyway, it's always, it's been a challenge. You can't. Go on. Yeah. That's too much. Yeah, yeah.
Yeah, this is yeah.
Yeah, so you could get what you want. Thank you. That's the way I
Integrated water, metal, chips, bananas, same logic, right? We-
Now, Cheetos have this.
Yeah.
Cheetos have C5. I never eat those because I hate this thing. Calories. Yeah. Actually.
you show the entire organization. However you want. You can say it to you, or you can edit it, or that time you want. Yeah. I'm going to just go right. Yeah, it pops out. That's awesome. Remember that the application is all on top of it. I usually just use the web version. Oh, do you? Yeah. Have you anything? Oh yeah, yeah. Send us something about that list.
If you go to the
Are you on Mac?
visual, no, it's
Okay.
go to is
The mode of web interface.
right. Notes. Is anything that falls below on the screen.
Yeah, I saw very similar problem with that on Macs, specifically with wasn't the web portal that it was the web portal. Was that stops on the bottom, bottom of the screen, and the screen is a time to do a full size of your display.
This one. Probably.
So
You can't look at it.
so it's all good size. First grade on the third was one of it. Yeah, I remember. His brother was Jason Porter was the one. Yeah. It's not just but yes. Yeah. Oh, they did put that on. So which one? Mac actually supports. Natively on inside of their remote connector. Yeah, actually, as a open supply, like do a bit more. Yeah, it's just fast. You should supply. Yeah. Yeah, I do that. I prefer actually now it's a hard
Call
You see? This stuff.
No,
And then it's
It's funny.
I haven't seen it.
I found it.
So what
Four times
is
in the I use Firefox. I use like mission control, multiple desktops.
Yeah. We're in the same boat.
Yeah, I didn't say never.
We just put it on there, so that we got 16 minutes. This is that chance.
Yeah. Yeah.
It's not a lot.
This is my favorite one.
I remember seeing it so long ago.
I don't know because it was funny because in the video I was all this is actually a screenshot of
Oh.
it's like the baby under the head.
Yeah.
Well, it was all my bed. It is actually also the first company that ever turned he does a lot of stuff.
Yeah.
But everybody in the movie. You know, it's not a good lost all the money.
Yeah, man, yeah.
Also, they spent $1 million to college. It's all pretty good.
Oh,
Yeah. Yeah, so,
yeah, the classic.
I don't even remember much about it except
It's
for
not
basic
my
miles.
basic idea.
Although, I would do it.
This is how bad the city
I like how we,
back together.
of course, nothing happens. There's our planet spewing out all the stuff.
Yeah. There's actually not a, they shot a lot of CG is falling apart. It really is what they want to build. Should we plan the
Yeah.
I'll send you down there. We'll get this show on the road. Did you? The symbol sign?
Yeah.
It's
not a slim person. It's not slim. It's so bad. Maybe I will.
I didn't know.
Do you have a, do you have
That's on it. You're on a training. It's not training.
Yeah, that was not what's happening.
I don't use
Yeah,
All I know about Atlanta, I know people draw that instead of
Oh, Atlanta,
yeah, exactly.
it's underwater. Yeah, I can imagine that. The aquarium is a lot more expensive than Coco. And, so I had to kill a couple hours. For Coco.
I love that. So, mechanical church,
I was there. I didn't get to go to Buckhead. I wanted to go to a couple of cool places on the list. But I went to Five Points. That was pretty cool. It's kind of like Coco versus Austin. Those are young funny. Yeah. Bunch of weird places with your bars. During, I actually left before that. Yes. Really quickly. I don't know where that happened. But, no, it was like that. I was thinking, I think they were 5 points to go. Yeah, I remember seeing them. Yeah. line by it. Yeah, like you got a line by that's got that, you got a line to get in. Got in, you got a line to get in the room. Get in the third room and then lock it up. And it's violating security. You can go on hackers. Then it's like a wall bill, like the screen lifts up, and it's like, whoa, 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 whoa. You get in there, and there's a line to go through the polar bear, the line to go to the bulb, the line to go to the factory.
Polar bear is it.
That page was.
After the movie, you have to in the lines for the entire. That's it.
That's something about. Happy this is not standing in line. Other processors go right in the barbecue and it's just like.
Oh my god. So you know that Twitter account that popped up, Franklin Line, or Franklin's Line, something like that?
It's in the building next to mine.
Yeah, that's my friend's sister. Like, her and her boyfriend started that, because they, like, overlook Franklin.
Yeah, are they in the 11 building?
So they just put the vibe.
Yeah, like, one of them people be home, and, like, they're, like, we put the wait time in,
I've been having
and, like,
a
already
good line.
You know, every morning up and down, there's always people in line. You know?
Yeah. Oh, yeah, no, everybody's like 2 hours early.
On Sunday, my friends went, and they got like 6 a.m. Thinking that they would be first. No, they were not. People in front of them were not there.
I have no issue with because of the time.
So what's more fun is go to the barbecue on 6th and Boulder.
Okay.
On the east side, it's close to Franklin, but it's still got to wait in line.
I'm
However,
just gonna go down to Lockhart.
Yeah.
One of those.
however, the barbecue is like beer and band. They're not just.
So it's kind of like hot dog.
Yeah.
What's it called again?
The barbecue. Yeah, on 6th and Boulder. Actually, have you been? You're not way more than 10 minutes.
It's okay. Most of the Ruby places are in gas stations, so it's kind of big deal.
No, that's the kind of deal. That's how that works.
You can't have Ruby without going there.
It's a shell.
No, my boyfriend's aunt and uncle live up in Central, and every time they come, they're like, oh, I think you can see them more often. Yeah, so I'm like, yeah, because they only ever want to go to the Ruby Festival.
Yeah.
The one like right off the Stampede track. Yeah. Like the one. Like good.
You never knew what it was. It's all wrong.
Never been there before.
It's pretty good.
We love our game.
I've never been there.
Oh, they have a branch now?
Yeah, they still do that. Yeah.
This, I 2 weeks ago, because I was like, it told us that 2 hours late. And then 20 minutes later, they call us. Like, oh, this information is a bit after. You was it then?
Yeah, but you can go out here and live up.
Yeah.
So one up here. Yeah, you just sit low. It doesn't have to go up.
Actually, Como on Palmer.
Oh, yeah.
Just past,
Yeah, I live on Stampede right now, so I'm not like good with north of the river.
This is really far north,
Well, when we move, it'll be,
not as far north.
yeah, I'll be.
No, but I live on the phone, it's like south of the river.
As when we first moved here, everybody was, I would tell people where we lived. After the grass and Canada, or south of the river. What's wrong with the cat boxes of south of the river? They still have them.
Yeah, but you want to live south Austin. They don't hang out this time.
And then we get drunk and around together on the floor.
Not staff.
think it depends on what group you enter in and you create. So it's like I'm older for the first because all the others are creating me on my card. Yeah. Like I don't go away from something.
I'm thinking of what else it is. 13 for not loud.
Yeah. It's actually really quiet, except you know, when the drums.
Actually, our favorite.
But everybody thinks at least it's quiet.
If they don't play it,
There you go. See?
you play it a lot. No, I'm joking.
We said that we got a house, so we don't have to. Do a couple of.
You sure was when you play drums?
Like, I used to go some things like.
For the Jack Studio or something. You should do a strict cutoff time. Way after.
It's always, like, it was always weird, like, school, so I went back, 3 to 5.
Yeah. Take that, right?
Probably.
But you still like couldn't play it without being loud.
Yeah, it didn't help. This pedal.
Sometimes they make you go
I'm not a good drummer.
so you convince yourself you can play by yourself.
Yes.
With my wife and
Walk around, that's
you have the, electronic.
I'm not a good drummer. I bought it for the price.
And our ice machine.
That's pretty cheap.
Get slides?
They're on here.
Are they?
They should be.
Okay.
They're the same slices that were.
Are they?
Yes.
Oh. I don't know. Yeah, of course. Let me find them. They do today.
Yeah.
You're good to go.
Okay, and where's my advance? Just that?
Yeah.
Okay. So let's start and talk about profiling. I'm Robert McClay, and we're going to your last pair of lectures, and then you can go home. I'm sure your brains are fried, so if you get a few things out of these talks, that's fine. I think the first talk on profiling really is about trying to use the machine more efficiently or trying to figure out where things aren't going well. And at least if you know that that exists, I've accomplished a mission. And then debugging, well, I make mistakes. I'm sure none of you make mistakes, but I make mistakes, and so debuggers can be helpful. Okay, let's talk about flops. One of the disclaimers is that counting flops has gotten harder and harder as we move forward. And what I mean by that is the manufacturers are very kindly putting instructions to count flops, only they don't count them the way you and I think they should. Because microprocessors have gotten way more complicated, and they get more complicated every time there's a new chip that comes out. There's a thing known as branch prediction, and so they're computing instructions and they're going to throw things away. And most processors count when they start a multiply or start an add, but they may never use it. So as far as you're concerned, you only did 100,000 flops or 1,000,000 flops, 1,000,000 floating point operations, but it may have counted 2 million because it started them. And they do it on issue, not on retire. That's what that means. So when an instruction starts, that's called issue, and when it completes, that's called retire. And they only count them, for reasons that are unknown to me, they count them on issue and not retire. So what you get is you get an estimate of how many flops you've got. And at least it's consistent, although actually it can get worse depending on how your memory accesses are. It might not even be consistent, but at least you'll get a scale. So on Lone Star, it's an older chip, and it can make reasonable estimates. Sandy Bridge can't count flops accurately. It's always an overcount, but it depends on how busy the system is. And the Xeon Phi, you can't count them at all. And the two machines aren't the same. Now, we are going to make a new Lone Star probably spring of next year. So I'm sure you've heard that multiple times. But machines aren't the same, but you have many of the same features. A few on Lone Star are IPM and MPIP, and then we've got Tau on both systems, and then the V-Tune amplifier, which is the Intel product, is available on Stampede. So, how do you time your code? Well, the simplest thing is just to run time on it. You can run time on an executable, and it will tell you all kinds of things about it: the real time, the user time, and the system time. So, the real time is how much time the whole thing took. The user time is how much the system thinks it would spend in your time, and then some of that time, say 10%, no, not 10%, about 5% or so, a couple percent is going to be taken up on system, because every time, because it's a time-sharing system, your process gets thrown out and something else gets picked up. So some of that time is going to be taken up by system. And you can get more information by, and it'll tell you how many about I/O and all that kind of stuff if you leave out the P option. Okay, and then so that gives you just, hey, how long my program took. The next thing are timers, which allow you, in the top one shows a Fortran implementation, and the bottom one shows a C implementation, and you can time your code and get timings on a block of code. And if you've got very coarse-grained timing that you need to do, I want to time things that you want to report to yourself, then this is a convenient way to do it. If you want more detailed information, there are other tools that can help. We'll get to them. gprof is the GNU project profiler. It's been around for a long time, and it's certainly one of the easiest things to get started on. And it provides various types of profiles: a flat profile, a call graph, and an annotated source. It's not as useful in parallel programs, but on a scalar point of view, it can be very useful. The flat profile reports CPU time spent in each function, self, and cumulative. So if you've got a child, if you're in a routine, a top-level routine, it may call lots of other routines. So the cumulative or the inclusive time will include itself plus all the children, whereas the self time will be just the time that you spent in that routine and not any of the children. Number of times the function is called, and it's useful to identify expensive routines. You can get a call graph, which gives you more detail, especially if you're working on somebody else's code or code you're not, familiar with. The call graph can be helpful. There are other tools out there that can do that, and you can even get, how many times a particular line is called. And we show you the 3 ways. Well, we no longer have the PGI compiler, but GCC or ICC, and similarly for other Fortran, that's going to generate a output file which you then have to, which is just a bunch of text or a bunch of data, which then you need to run the gproc program on to actually see what's going on. And so here's the flat profile that shows you in the main routine you spent 50% of the time 2.5 seconds. There were 2 calls, and the call to it calls the mat sort and so forth. And so it gives you the time, from the most cumulative time to the least time spent. So like in vector cube, almost no time is spent at all. And you can get a call graph which tells you, way more detail about how the thing is structured, how your code is structured, how it was called in runtime. And so you've got a visual call graph that shows here's the main routine and all the things it calls, but you can see that there's the main calls this main squirt, the main squirt from 2 different places. So it gets called by the main program, also calls by system squirt, and again you can see that this vector square root is called from 2 different places as well. So that gives you, that's sort of the lowest level, but the easiest thing to do. All you need to do is do a -PG to get gproc to work. But gproc is going to be really good for scalar programs. I'm not sure it's going to do much help with threaded programs either, but it gets complicated in parallel. So we've got more tools that help you. PerfExpert is a brand new tool that's developed here at UT. So one of the persons who work on it is actually here at TAC. It's designed to be easy to use and understand. It's great for quick profiling and for beginners. It has recommendations on what to fix. It collects data from PAPI through HPT Toolkit. Okay, 2 buzzwords. PAPI is the Performance API. So it's actually it has kernel routines that talks to and actually gets hardware counters. So that's nice, that it will tell you how many cache misses you have and an estimate of the flops, as I said before, and other kinds of information about that. And then HPC Toolkit, and many packages use PAPI to get hardware information. HPC Toolkit is one of them. But it doesn't tell you about, PerfExpert doesn't tell you about MPI, no 3D visualization, no elaborate metrics, but it's designed, combines ease of use, interpretation, and it makes optimization, and it makes optimization suggestions. So this can be useful when you don't have 20 years of experience doing this and knowing where to go fix things. You've been exposed to the module system, and so you need to access it. You need to load the PAPI module and the PerfExpert module. Then you compile it with full optimization, and then you run it with PerfExpert. And PerfExpert, then you can use it to, you run the code, you run through PerfExpert, and then you run the PerfExpert tool to visualize what your results are, and you can get information about how the programs run and all that. So I should have mentioned that PerfExpert, well, gproc and PerfExpert are sort of samplers. They're not actually putting in timers in your code. You know, this routine got started here, ends here kind of statements. It's more, it interrupts the code and says, hey, I'm here. Hey, I'm here. So it's getting a statistical estimation of what's going on. So it finds, so routines you spend a lot of time in, you're statistically more likely to be in that routine and routines you spend a little bit of time in, you're statistically likely to be in them less. So you get an estimate of how much time you spent in these things, and that's a convenient way to work. It doesn't require any extra work on your code. You don't have to compile anything in. You don't need to do a source-to-source translation or other tools. There are other tools that do that, give you that very fine-grained control. It also, so you can run it. You can select autoscope for optimization suggestions, and you can make suggestions and run autoscope again. So you can use this as a way to iterate through your code and make improvements in the performance. And it can make optimization loops. So maybe you've got the loops. Maybe you've got the loops organized I by J, and it would work better J by I, and it makes recommendations about that, and about loop blocking, and making your loops less complicated, because sometimes you can use the hardware more efficiently in that way. So a tool that's only available on Lone Star is the Integrated Performance Monitoring. It's a quick and easy and concise tool for profiling. The level of detail is less sophisticated than Tau, PAPI, or HPC Toolkit, or Scholastica. It provides portable profiling infrastructure for parallel codes, and provides a low-level performance summary of communications and calculations in a parallel program. It's designed to be easy to use, low overhead, scalable. Scalable is important because you'd like to measure your code, and you'd like your performance measuring tool not to suck up all the cycles so you don't measure things correctly. It requires no source code modification, except that you need to put the -G option to put in symbols. And it produces an XML output that can be read by browsers. It's available on Lone Star. Ranger no longer exists. Well, parts of it are still here, some of it in South Africa. You need to load the IPM module, and then you can follow these instructions and run your code. And you get an IPM report, which is either full, terse, or none, depending on how much. You set these variables to say how much you want, and you can find out more about how this works by running the module help IPM command. I'm pretty sure it is, because it has to be, because it only requires no source code modification. So there's got to be a sampler. Okay, and so here's telling you all about the time you spent in various parts of the routine. It reports hardware counters, PAPI, FP ops, that's the number floating point ops, total cycles, vector instruction, total instructions, total cycles and total instructions, and then it reports how much time was spent in those 8 MPI routines. And then you can get this very pretty output describes in a pie chart that's showing you that, hey, your communication time was all spent in MPI all reduce. And the next one is the broadcast. So you may want to think about the design of how you've built your code, although sometimes you're just plain stuck. And you can get all kinds of information, how many times it's called, what the buffer size were, times, and all that. And you can get more detail about task timings, flops, and calculation balance by task. So you can see that processor 0 is doing way more work than processor 64. And you can see, you can get these graphs to tell you how much time you're spending in each of the major MPI calls. And distribution of, same kind of information. And the topology. So you can see you've got some sort of, looks like some sort of 2D partition of the data. Okay, but what's nice is you can use this tool to find out, quick tools are good to find out where you're spending most of the time in your code. That way, usually, the usual rule about 80% of the time is spent in 20% of the code applies, especially to numerical codes. It's usually the solver. But depending on what you're actually doing, And it's helpful for doing scaling studies, both strong and weak, so you can see how well your code is scaling as you add more processors to it. And you look at the communication pattern and see how your communications is compared to your compute time. It's not the answer when you already know where the performance issue is and you need detailed information about how your code is. This is sort of a first cut, but when you need to know more, this is a place to start, but not a place to end, which leads to the advanced profiling tools. And these are the advanced profiling tools can be intimidating, especially if you install them yourself, because they're difficult to install. They have lots of dependencies, and many times they require a kernel patch. But fortunately, we've solved that problems for you, and they're useful for both serial and parallel programs, extensive profiling and scalability information, and you can analyze the data, and it also be able to talk to the hardware counters, but it does use function wrappers. So PAPI is the low-level tool. It typically requires a kernel patch or something kernel aware, so that you can actually access the hardware performance counters. There are registers buried in the processor, which you usually need a privilege call to make. So you usually have to go through the kernel. But the nice thing is, as PAPI is available on Intel chips and many, of the IBM Power Series, the Crays, and lots and lots of different computers. Of course, the world these days is mostly running Linux. running some sort of Intel chip, so you're covered. And it's available on both Lone Star and Stampede, but it's be aware that the flop counts aren't going to be accurate. Some worse than others. So Tau is one of the tools that we use. I've used this tool many times to get an understanding of somebody's code. It gives you lots and lots of detail about it. It can give you per routine instructions. It can give you, and you can also do some very sophisticated analysis of codes. The big problem with Tau is it's a pain in the neck to use, because what it's doing is it does a source-to-source translation. So it's actually taking your code, trying to understand enough to put in, here's where this routine started, here's where it ended, and here's where it jumped into a subroutine. So it has to do a source-to-source translation, and that doesn't always work. But that's okay. If it's limited to a few routines, you can say, hey, I'm not gonna collect data about this particular routine. The other problem you run into is that these timers can be expensive, so that if you time routines that get called millions or billions of times, you may spend more time in the actual timer routine than you actually did in the routine before you put the timer in it. But fortunately, Tau gives you a tool which says, hey, don't time this one. Don't modify this source code. It's been around a long time. It's got great performance tools, and it's gotten easier and easier to use as time has gone on. And what's nice is it provides some really great analysis tools, and it's easily visualized. It understands parallel programs. It's one of the really, if you really need to know what's going on, Tau is one of your places to go. And we have projects here to better understand users' code, and Tau is the tool I go to when I need to do that. It does support call graph and call path profiling, and you can even say I only want to keep track of this particular section, so you can break your code up into phases. And how it does is use this thing called PDT, which is the instrumentation part. So this is the part that has to work in order to get more information about your code. So you have to run the source-to-source translation, and it means changing how you build your system and replacing the, if you're using MPICC or F90 or whatever, you need to replace it with these shell scripts, and then that's how you have a hook into say, hey, don't do instrumentation on routine A, B, and C. Do it, and don't do it here, and don't do it here, and do everybody else. It really works well with MPI. It doesn't work quite as well with OpenMP. And the way you do it, is well, there's a couple ways to do this. The easiest way to do it is actually just go in and modify your make file and replace those compile lines with those pieces. That's how I do it. But there's other ways that they've tried to make it easy to do, and you can control the options. Here's why you go through all that trouble, because you get all this information about, various counters. You can find out where the routine is spending the most time. You can find out whether you've got balances. One of the problems you have in parallel programs is you may have one or a few processors spending their time doing all the work there and no place else. So Tau is a wonderful way to help find that out. The other thing you can do is you can use one set of counter to build up other set of counters, so you can do some arithmetic to be able to visualize things in terms of other parameters. And you can get, the time, the thing I've found, Musha, actually is to know how much time you spend in each routine, and also getting flop counts, just to find out hey, here are the big routines. One time I analyzed a client's code, and they had 700 barriers in it. In the call, and so when I got the call graph, it said all the time was spent in barriers. Like, wow, I mean, that's pretty bizarre. But you can get all kinds of useful information out of Tau, and it's worth the trouble, or it's a lot of trouble, but it has great results. Okay, what else? You can get things like data cache misses. L1 misses, L2 misses, TBL misses, all kinds of things help you think you want to structure your routine. Again, you're going to want to spend, only a small percentage of the routine should be the place where you're going to make these kind of optimizations. You don't want to rewrite the entire code.
Sorry,
yeah.
I think this is a totally normal question. What's a mix?
Well, okay. Memory's structured. So you've got, the only thing really happens is at registers, right? You can only really do arithmetic between registers, so you have to get the data there. So we now have what are known as L1 caches, L2 caches, and L3 caches. So if it's found in a cache, that's a hit, and if it's not in cache, it's a miss. And so so stride 1 access is usually the keys to the kingdom, if you can get it. So because when you say, I want this location, 10. Well, the way all microprocessors are designed these days, it gets 10 through 14. And so if you pull that data in, then a whole line of data is going to be pulled with it. So when if you ask for 11, it's in cache. So you pay for one miss. You pull in lots of data because that's efficient to be pulled from memory, and then it's in an L1 cache so that when you go, it's in a place. It's in my little box here. Oh, I've got it. I can pull that one out. Oops, it's not there. Can you get me the file over here? I've got like I'm in an office and I have a file drawer that only has a few files in it. I can pull things out of that drawer all day, but I need help when it's in another room. So that's really but when you went to go get that file, you didn't grab just that file, you grabbed all its neighbors. And you bring that to me, and then I can use those files because I'm working through it. But if I say, okay, every time I got to go to main memory, that's many and many cache misses. So the hardware, while memory is pretty fast compared to disk, say, main memory is slow compared to L1 cache. So you pay you might get the next point with one or two cycles, where it might be 50 cycles to get one out of main memory. So that's why knowing how many misses you have is useful. Good question. And you can do derived metrics. So you can divide. For example, this last one shows floating point operations divided by L1 cache misses. and that could be useful when you want to figure out what the hell's going on. Okay, so that's the public domain piece of software that's out there, that's available in lots of places. You can run it on your laptops, you can run it anywhere. vTune is a tool that comes from Intel. Comes with, well, it sort of comes with the compiler. It's an Intel product. It's free for non-commercial use, and you can load it on Stampede with the load vTune. It will support profiling on the mic on the Xeon Phi. It has a two-part interface, a command line and a GUI. It knows about MPI routines in that they're like any other routine, but it doesn't understand MPI ranks for per rank profile results. It's a three-step process. You compile your code with -G in full optimization, run this amplify CL to collect information, and you can visualize it with the GUI. For non-MPI codes, that line, that second to last line shows you how to do that. And then for MPI codes, you'll need to run it with run the amplify CL code through IV run. It provides CPU frequency. It provides a lot more data, and it's got this very beautiful display. The speed getting it to show up has been problematic, but it is the only tool that's available to tell you anything about what's going on the Phi. You can collect data. I don't know. I'm getting bored with this, and I just got started. But basically, this is this tells you a lot of information about Xeon Phi, and you can learn that. And it does have a nice web page to show you information and show you where you spend most of your time in routines, from largest to smallest. All right, let's go back. So, profiling. Profiling is a process that takes time and effort, and it can tell you a lot about what your code's doing. And it's important to, the most important rule is not to optimize before you get started. Donald Knuth, a famous computer scientist, has said something like, the root of all evil is premature optimization. And I have certainly decided something's going to take a long time, and turns out it's not the thing that takes time at all. I'm always surprised. But the only other thing that you can say is once you're ready to tune, you're going to have to, you have to measure it and then come into with an open mind and say, oh, this is where I'm spending all my time, rather than the places you thought it might be. And you want to profile for typical cases. The one case you never run is the one you want to optimize for what you normally run. You got to do it. You got to test with the thing in full optimization mode, because otherwise you're not going to get the right performance, and you need to test for scalability, because that's the only way we'll let you into the bigger queues, is to show you that your code scales. But you can't always assume that any change you make is going to be improvement. Sometimes they don't. And you may want to profile some atypical cases, but you can't profile forever. You got to have a life. So spending a little bit of time can be a big help. Spending forever is not going to be useful. So set some goals and/or a time limit. There are lots of other tools out there. So Tau is the one tool I've spent a lot of time in. There are others, Scholastica and HPC Toolkit. I want to mention Scholastica as having is both better and worse than Tau. It's better in that it doesn't require a source-to-source translation. It actually, the compiler writers have given you some hooks so that you can, rather than having to modify the source code, it gives you, if you give it some magic flags, it'll call a routine for you with an address that it got, so you don't have to do the source-to-source translation to put in the timers. The disadvantage of Scholastica is it doesn't have as much of the beautiful graphics that Tau has in the way to do derived analysis. This measure over that measure. Okay. So that's it for profiling. Any questions on profiling before I switch over to debugging? Debuggers.
For you. The other one play.
Debug is the top. Thank you. Okay. We're on the final stretch. I probably will be definitely done before 4:30. I know that the end of 2 days, I'm sure your minds are mush. So I've really only got 3 topics: GDB, DDT, and PTP. So before I start talking about debugging tools, I want to spend a few minutes talking about debugging. Debugging tools are great. They're a wonderful thing. They're like magic. And it's really nice to be able to step into a routine and start watching things as they change and say, I didn't mean that to happen. Why did that happen? And debuggers are great for that when you know something. But the trouble is sometimes you don't. You don't know where a code's failing. You don't know anything. And so sometimes putting in print statements can be a faster way to debug. And it's going to be a personal thing. You can get lost into stepping through a code. You know, it can take a long time to get where you want to go. So depending on where you are and how mature the code is and how well you understand the code, print statements can be really useful and worth thinking about. Also, designing your code for debugging can be something you need to think about. One of the things that I like to do is I like to have a way to do logging, a way to say, hey, this routine got called, that routine got called, I left this routine, some way to trace the behavior that can be, if you can add something like that, can be a real boon to say, hey, I've made it through all this stuff and I'm now stuck in someplace in here. That can be really useful. I do that for a lot of the interpretive codes I write where I don't have good visual debuggers. So let's start talking about the tools. GDB, well, let's start on GDB. You got code, you got bugs. One of the troubles you have is if you have print statements, if the code dies, you may have printed something, but the buffer didn't get flushed. And so you got all the way down here, but you think you're up here because that's the last time the buffer got flushed. So sometimes you may have to slow down the performance by telling the code you want to flush all the buffers. But the nice thing is you don't have to do that. You can use tools like GDB and DDT. They're accurate and they do make finding errors a whole lot easier than putting in multiple print, compiling, putting in a bunch of print statements, then say, oh, I got this far, it failed here, oh, what, So, and then you've got to take that stuff out. GDB is the GNU project debugger. It's been around a long time, and it's really great for serial codes. You need to compile. Your best bet is to compile with G, -G, and O0, because while you can debug optimized code, it can make you feel like you're drunk because it's jumping all over the place because it's, the compiler has restructured your code, and so it's not following the logic that you put in it. So O0 typically is what you want. Although in a pinch, you can try it with O3, and if that fails, then recompile with O0. And then you can use the GDB -D on the source directory and the executable file to tell the debugger where your source is. And you can tell it to be quiet. And inside of it, you can type help to figure out what your commands are. There's 2 levels of control. You can run your code, wait for it to crash, and then put your code in the debugger, and it'll tell you where it failed, and you can get a traceback. Sometimes that could be really handy. But you also can start the code inside the debugger and set breakpoints and tell it to, okay, stop at line 47, but run, and then run until you get to the breakpoint. And then you can set up print statements that'll print out at at breakpoints, or watch. You can watch specific variables. Now, watches are expensive because essentially there's an interrupt that happens every line to say, hey, did this variable change? So if you're doing 1,000,000 times, that can be expensive. You may want to, what I call doing a binary search on your code. So if your code is this big, run it halfway and see whether something has changed, something you want to change, and then do this. You can get to where your code is failing fairly quickly if you're willing to run it 4 or 5 times. You can find out where something has changed. That may be faster sometimes than putting a watch point. Depends on the size of your code and how complicated it is. Try the watch points first, but if that fails, then think about doing it the binary search way. Lots of commands. You can tell it to run or kill the program. You can tell it to continue. You can step 2 different kinds of steps. There's actually a step and a next. I think we discussed the distinction between that. So step typically means if you get to a call statement, step says step in, end says run that routine as a single step rather than stepping into it. You can print variables, you can list, you can set breakpoints, you can set watch points. And the point is you've got, here's a GDB example that has both either a C code or a Fortran code that's failing in basically the same way. It's going to do a divide by 0. No, well, it's got an undefined variable. Well, it's going to get to a point where it's going to divide by 0. So you run your code, and it runs, and then it tells you at line 28 in the C code, it's failing when y equals 5 and x equals 5. When you do the return statement, you've got to divide by 0, so it crashes. And it'll tell you where, so it tells you that it died when you called this my division routine at line 19, and it failed at line 28. And you can step through the code and find where these things are, and you'll find that these 2 values equal, and then you can kill and quit and then fix your code. One of the things that is interesting is okay, so printing out a single variable is typically something you're going to want to do. Or you can tell it to print out a vector or an individual copy of a vector, or you can tell it you want to print out consecutive entries in a vector. You can do that both in Fortran and C, or you can print out a matrix. But what happens is, well, it gets complicated when you want to print out a if you want to print out more than a single value in an array or a vector, you have to use this @ symbol. So you say, I want to start at A of 10 at 100. So we'll print out the, from 10 to 110, those values. And you can do that for both vectors and matrices. But when you're writing out, when you're doing this, you're going to have to write it out in, if you got a vector, a 2-dimensional array, you're going to have to do it in the stride 1 direction. There's no way to print out columns or rows in Fortran. Some debuggers, and well, not available in GCC, but it's available in others. Oops, that was getting my talk done faster. Okay. So you can get information on breakpoints, where the breakpoints are. One of the things you can do, which is nice, is you can set a breakpoint with an if test in it. So you can say, I want to run this test till x equals 5 or something. And then you can enable or disable breakpoints, so you can have one and turn it off and then turn it back on, or you can delete it, or you can say, hey, get rid of all of them. You can also attach to a program that's currently running. And one of the things that you can do on on our machines is you can, when your job is running, you you have access to the compute node, so you can log on to it, and then you can attach a debugger to it and see where on that node where the code is failing or where the code is hanging. So you've got a way to attach to a particular your program as it's running on the compute nodes. So you can use GDB to find out, at least for one of your tasks, what's it's doing. Oh, it says right here. You can get in the queue. You can get there and log on to that machine. You can use QStat to find out what machine you're on, and then you can log onto the main node. So GDB, the summary is, you compile with -G, -O0. Then you run GDB with the directory and source, and then you can step through your code and find out where things have gone awry. So we have a commercial tool, DDT, which is my favorite tool. It's multi-platform. It supports MPI, and it's able to scale to large OpenMP and MPI. It's got memory checking and MPI checking, and it's got a very useful graphical interface. Comes from Millennia. The way it works is you fire off DDT. You can fire off DDT and then wait for it to get into the queue. You give it an application and arguments. You can specify general submission things. Let's see, where's that? Right here. You'll have to set the queue. You must set your project inside of the DDT parameters. And then you've got a project window, a code window, a variable window, a stack window, and an evaluation window. So the way I'm typically working is I've got the code up in the center panel in the code window, and I'll create values I want to track as the code goes through in the evaluation window, as well as looking at local variables line at a time in the variable window. And you can click on, you want to look at task 0, task 1, task 2. You can switch at see variables. The nice thing, this slide is a little old. The new version will tell you what the value. It'll give you a stair-step chart to say what's this value across all the tasks. So if you see a straight line, you say, oh, all the values are the same across all processors, or if it jiggles, you'll know they don't have the same values. And that can be very helpful, very quick way. You got a question? The way you run it is you do a way you run it is you do a modulo DDT, and then you say, if you're on the front end, you can say DDT, you put together you say, is it DDT and the name of your executable, and then a window will pop up. You can say DDT, the name of the executable, and the arguments that go to your code, and then you can run it. And then what it'll do is it'll put it into the queue, and you'll sit there and wait until your job is actually started, and then it'll come back and tell you, hey, you've now got control of your job. Yes, yes, and so typically you're going to want to run. So, as true with most debuggers, while you may be able to debug lots and lots of tasks, it gets unwieldy. You really want to debug at 4, 8, 16 kind of, maybe 32 kind of sizes rather than 1024 or 16K or whatever. Okay. So across the top, you get information like, how many processes you've got, and all that, and you can click on various sources and put breakpoints in. You might want to set a breakpoint in a source that isn't up, so you can go find it and then go set a breakpoint and allow the code to run till you get to there. And you've got this bottom lower left window tells you where you are in each routines, or will tell you what the output is, so you can see what's gotten printed to either all tasks or individual task. So I find it to be a very useful debugging system. I've used it a lot. You can also track things like memory leaks and memory usage. And in this particular graph, you see that process 0 is using way more memory than all the other processors. So now that might be the way your code works, but it may also be there's a memory leak in processor 0. Yeah, and this shows you how to do it. So you log in. The important thing is you need to have X forwarding on. So this minus capital X, log in to Stampede or Longhorn, build your job up, load the DDT, and then DDT and the executable. If your executable takes arguments, you'll need to add that there, or you can fill in the graphical interface, and then you fill in the what MPI stack you're using, what the Q parameters are, and you can turn on memory checking. Okay. Last one. Eclipse PTP is, well, Eclipse is a program developing, IDE. I don't use it. I don't have a lot of experience with it. I have people around here who love it. It's free. It's available as part of XSEDE, and they get answered by people who work for XSEDE. It supports rote development, so you can develop on your local workstation and then run remotely. It's got interesting features like refactoring code compilation, static analysis. It's collaborative code development. So there's lots of features in it. I feel like I'm looking like this through my code, but to each their own. It has it sort of looks like a debugger to me. So you've got a big panel which says on the left it tells you where your source tree is, and in the middle panel it tells you about your routine, and then it gives you at the bottom, it tells you things like when you compiled it last where all the errors are. It does have some interesting hooks. It knows about the language, so it can do some interesting things and learn about, help you, tell you things about your code, because it's knowing things about like that my rank is an integer and has a value of 0, so you can run it. You can run it in the debugger, which is what this window shows, so that it is also a debugger, and it can be running on your machine and connecting remotely to the system. Let's see. You can, choose, well, depending on this, what this slide shows, using OpenMPI on Lone Star. Yeah. So debugging is, something where, if you write code, you're going to end up debugging it, unless it's 3 lines long, even though I've screwed up 3 lines. You want to debug your code if it's erratic, doesn't get what you want. One of the things that can be hard, one of the biggest pains is when you get what I call a Heisenbug. You put in a print statement in your code, and it was broken before you put the print statement in, and it starts working. And what that tells me is that I've got a memory leak. More than likely, I've got a memory leak, or I've got my arguments. I have a in Fortran. It's easy to have a wrong number of arguments between one routine and another, because it's easy to have no checking. Although it's now gotten better, but you have to write for it. But it's easy to have pass the wrong thing in, whatever. Sometimes the program will hang, and it could be that it's not hung, it's just sitting there doing something that took a lot longer than you think it should. Or it could just plain hang because some communication pattern, you've got a deadlock. But you're getting bad results. You're getting not a number or infinities when you shouldn't. You're going to have to find ways to debug your code. One of the things that that I enjoy doing or have done a lot is testing. And this isn't a testing talk, but testing is part of debugging. When you debug something, you've got an expected output which you're not getting. Now it might be you got no output, but but you didn't get the output you expected. Either it was none or it wasn't the right one. So one of the things that I want to put a point is that designing for testing can make your life debugging a whole lot easier because you know what you're expecting to get. And at some point I'm going to talk about that again. Anyway, any questions on the debugging?
So for DBT to work, you just compile it with text.
-G is all that's required. -D00 you probably find a little bit easier to debug your code because it'll, you'll be doing it. It can take a while to get to the point where you think it is because you might jump into what you think is the middle of an if statement, even though the if statement isn't turned on. It's because the code has been optimized in ways that can be hard to understand. So, and sometimes variables you want to track have been optimized out. You can't get their values. And so without doing with O0, you should get the values, although I've seen some compilers screw up on that. Sometimes I'll actually switch from Intel to GCC to debug, or switch from the Intel compilers to the GNU compilers, even though they're not necessarily faster. Usually they talk to the debugger better. And because DDT sits on top of GDB. It's actually using GDB to talk to the system, so that way they don't have to understand the low-level details. And Intel's gotten better, but at one point, debugging Fortran with the Intel compiler was just awful. I think it's a lot better now, but it used to be a disaster. So stay with the Intel compiler, but if it doesn't work, then remember you can change compilers. And switching, and that's another thing which we don't talk about as much, although we've made it easier on the system. I know because I wrote it. Switching compilers can be a useful thing to do. Sometimes you'll find something out with a different compiler just because it's not the same, and it may give you insight into how your code's working because the GCC compiler and the Intel compiler will do different things, and it may tell you something that you didn't know. Okay? Thank you.
Yes, sure will.
Yes.
And that's what's the only reason I got through that scientific program.
Because of the debugging lecture? Because of debuggers?
No, by switching the compiler.
Oh, really?
How they compile differently to find the bugs in my program.
Yeah.
The only way I successfully debugged 2
I'm sorry, we don't.